Last week we started with lecture 9, receiver characterization. We had to stop because of a technical issue that we encountered. So today we continue with lecture 9, receiver characterization. And as I said before, receiver characterization gives the basic information or knowledge that one requires, excuse me, that one requires in making a judgment about what radio receiver to procure. So some of the parameters that are investigated receiver noise, receiver sensitivity, system nonlinearity, receiver dynamic range, and receiver selectivity. So last week we've gone through, we've been through receiver noise. So I'll just brush over very quickly and then we move on to the ones that we are yet to have a look at. So we looked at receiver noise and the relationship between the channel, the bandwidth, and the signal to noise ratio. So from the Hartley-Shannon theorem, we know that the channel is equal to the bandwidth times logarithm to base 2 of 1 plus signal to noise ratio in bits per second. And as we discussed before, so the Hartley-Shannon theorem relates the channel capacity to the channel bandwidth B and the signal to noise ratio. And there's usually a trade-off between B and signal to noise ratio. And this trade-off between the bandwidth and the signal to noise ratio can be very easily understood from the way GSM systems are designed versus the way CDMA systems are designed. If you look at the way GSM system is designed, it operates at a lower frequency compared to CDMA. And because it operates at a lower frequency, it will usually have a bandwidth which is a fraction of the frequency that it operates, which we call the fractional bandwidth. Now, this bandwidth compared to that of CDMA will be small. And as a result, in GSM, you need a much higher signal to noise ratio so that your delivered signal will be intelligible. In other words, for good channel capacity and therefore fewer errors and therefore good outputs at the receiver, you need a higher signal to noise ratio because the bandwidth comparatively is small. Alternatively, in CDMA systems, because it operates at a higher frequency, then even with a lower signal to noise ratio, it has a good channel capacity. So because it operates at a higher frequency, the bandwidth is higher, and because the bandwidth is higher, it means that the signal to noise ratio can be lower. And in fact, in CDMA system, the signal to noise ratio is so low that sometimes the signal can be just beneath the noise level, but it still can be intelligible because there's good channel capacity. In addition to a coding mechanism that helps reduce errors in transmission. And I'm sure you came across some of these coding mechanisms when you were studying information theory in the first semester. And yesterday, for example, there was a news conference by the Minister of Communication to the extent that they are giving the two major telecom operators, which is Vodafone and MTN, they are giving them extra bandwidth or spectrum for free for 3 months. Why was that necessary? Because many people are at home and they are on the internet nearly 24/7. So the amount of traffic on their channels has increased tremendously. And if that is the case, from the Hartley-Shannon's theorem, it means that they are exhausting their bandwidth. And if they exhaust their bandwidth, then you're going to have a lot of difficulties in communication, either errors or high level of blockage. And you know this from switching engineering also. And so they needed more frequency or more bandwidth to be able to carry more traffic. That is a higher channel capacity, which is what you saw in the press conference of the minister yesterday. Okay, so talking about receiver noise, which is the first item that we are looking at in this characterization. The source of noise in a receiver comes from, number one, the channel, and we discuss what the channel is. The channel is not it's not really the physical medium. It's not what we're referring to as a channel. When we say the channel, the physical medium is a contributor to the channel. But a channel is a model of everything that happens to the signal from the point when it is emitted to the point when the signal is received. And therefore, the physical medium, yes, contributes because it also adds noise and other effects, including attenuation of the signal before it is received. So the channel through to the antenna contributes noise. The RF preselector filter. So to be able to detect the desired frequency, there must be a filter that allows only that frequency to come through from the antenna, which is called the RF preselector filter. And there is some thermal noise contribution from this filter also. The active devices, in addition to thermal noise, also give other noises that are called the shot noise and flicker noise. Flicker noise is also called the 1/f noise. Now, flicker noise is most important, especially in oscillators and sometimes mixes. But the most dominant noise in the system will be the thermal noise. Of course, in addition to the noise that is coming from the channel in the form of naturally occurring noise and galactic noise. That is noise from the galaxy. And then we saw that the thermal noise power, Pn, is given by the product of the Boltzmann's constant, which is K, times the temperature, which is T, times the bandwidth, which is B. And for such an expression of the noise power, the minimum noise power will be obtained when B is equal to 1 and T is at the standard temperature of 293 Kelvin. So bandwidth of 1 Hz and 293 Kelvin, and Boltzmann's constant, which is a constant, will give you a noise power of 4.057 times 10 to the minus 21 watts. This noise power in dB is equivalent to minus 174 dBm. And this minus 174 dBm is if you want the minimum noise that you expect in every radio system. So that will be the minimum noise. And sometimes the minimum noise in that radio receiver is referred to as the noise floor. So how do we characterize a receiver's noise? We characterize the receiver's noise using a factor called the noise factor. What is the definition of the noise factor? Before we look at the definition, let's look at what happens with respect to noise in the radio system. So you have the desired signal, which is SI, and the desired signal, as we spoke about earlier, comes with noise from the channel. So this is the input signal SI, and this is the input noise NI, and they come together, signal plus noise, which is how we talk about the signal to noise ratio. What is the amount of signal compared to the amount of noise? So this comes into the system, but the system itself will add its own internal noise. So this internal noise added by the system adds to this incoming noise, and then it's amplified, and that becomes the output noise N naught. And then the signal Si also is amplified, and we get the output signal S naught. If it were not for the internal noise Na, then the ratio, signal to noise ratio at the input, will be exactly equal to signal to noise ratio at the output. Because the signal, the incoming signal Si is amplified by the same amount, G, as the incoming noise. So it means that Si and Ni will be scaled to the same amount, barring system nonlinearity, and therefore the ratio would have been the same. However, the system itself adds its own internal noise, and therefore N naught becomes significantly higher than the input signal to noise ratio, than the input noise, sorry. What it means then is that the input signal to noise ratio will degrade by the time it reaches the output to the detector, because now there is more noise than there is signal. So there's a degradation of the signal to noise ratio in the system. And that is exactly the definition of the noise factor. The noise factor is a degradation of the signal to noise ratio from input to the output of the system. So how do we express that? We express that as F equals N naught, which is the output noise, divided by the input noise, which is KT naught B, times the gain, G. And we can manipulate this equation to come up with a very simple definition that reflects the explanation we gave for the signal to noise ratio. So for the noise factor, i.e. the ratio of the input signal to noise ratio to the output signal to noise ratio. So how do we do that? If we multiply the numerator and the denominator by Si, so we have Si in the numerator. In the denominator also we have Si. But that Si times G here will give you S naught. So we have G times Si, and that is S naught. So we have N naught Si divided by KT naught B times S naught. Now we note that Si, which is the input signal, divided by KT naught B, which is the input noise, will give us the input signal to noise ratio, Si over Ni. And then we have N naught divided by S naught. If we divide it, then it becomes S naught divided by N naught. In that case, this becomes the output signal to noise ratio. And therefore, the definition for the noise factor is a ratio of the input signal to noise ratio divided by the output signal to noise ratio. Alternatively, it is a degradation of the signal to noise ratio from the input to the output. And if expressed in dB, then the noise factor is called noise figure, which is usually the most common or the commonest way that the noise performance of a device is expressed, which is the noise figure. Now we could have a cascade of system, and a cascade of system, in that system, every device or circuit in that system will have its own noise factor and its own gain. This gain may be lost in passive circuits, but it will be a gain in active circuits. So you have a combination of circuits that forms a radio system, and these circuits are cascaded. And so the total noise factor is as a result of the cascade given by this equation here. The first element or the first parameter here is the noise factor of the first stage of the radio receiver, F1. And then plus the noise factor of the second stage minus 1 divided by the gain of the first stage, all the way to the last stage. This equation can be driven, but we skip the derivation and simply just quote it. Then the next item we look at is the receiver sensitivity. The receiver sensitivity tells us how good a receiver is in detecting incoming signal. And how good a receiver is in detecting incoming signal will be determined by the noise floor of the receiver prior to detection. In other words, what is the underlying noise in the receiver? That signal that is incoming must be slightly, at least, higher than the noise floor of the receiver in order to be intelligible. And mind you, the incoming signal will also come in with its own internal noise. And therefore, the noise floor of the receiver will determine how strong the input signal must be in order to be detected correctly as either 0 or 1 in a digital system, or as a high quality analog waveform in analog system. Therefore, the receiver sensitivity is defined as the minimum input signal strength to produce quality output signal in the receiver. That is a definition for the receiver sensitivity. Now, we spoke about the noise floor of the receiver. If this is referred to the input, that is, you take out the effect of the gain of the receiver. If you look at here, see, at every stage we divide by the gain of the receiver. If we take it to the input, then it means we are taking out the effect of the gains of the receiver. Now, that's noise floor of the receiver referred to the input is called the minimum detectable signal, and it is used as a measure of sensitivity. In other words, what is the level of the signal, the minimum level of the signal for the receiver to be able to detect it. And in general, signal to noise ratio of 10 dB is considered minimum for audio files. And therefore, it is used as a measure of sensitivity. Another measure is SINAD, signal in noise and distortion, also of 10 dB. And the other one is bit error rates of about 1% specified. But now some systems will require a bit error rate of better than 1%, especially in very sensitive transactions like banking transactions, for example. In banking transaction, a bit error rate of 1% means that out of every 100 symbols that are transmitted, one symbol will be in error. So either a 0 will flip and become a 1, because you know for a digital signal, this is the way it is. Let's take a very simple binary signal like this. So an error means if there are 100 of these symbols, this is 0, this is 1, and this is 0. 1, 0, 1, 0, etc. So if there are hundreds of these symbols, a bit error rate of 1% means that of the 100, one of these symbols, either a 0 can flip to become a 1 because of errors. So if there are errors and noise like this, so this is supposed to be 0, but the system will see that as what? A 1. And therefore the 0 flips to a 1. So 1 out of 100 is a bit error rate of 1. And that is usually specified. But I'm saying that for very sensitive transaction, security, banking, and things like that, sometimes a 1% bit error rate is even not good enough. And a much lower bit error rate is specified. Now, one other thing that we should talk about relating to very practical situation is that the receiver sensitivity is so important. It determines how, or it determines whether or not your receiver can detect a particular signal or not. So two of you can be within the same location, just probably be a meter or two apart, but one will have good signal level and the other one will have less signal level on their phones. And if two people were to call the two of you, one of you may receive the call, but the other one will report that the phone is switched off. Why? Because you probably be at the edge or towards the edge of the cell site where the signal level is weak, and because the sensitivity of the receiver of this other person is very poor, he would not be able to detect that signal. And these are the things that explains it. The other one is system nonlinearity, a very important parameter of the system. And what is system nonlinearity? A component is nonlinear when its input amplitude is not linearly proportional to its input amplitude. When its output amplitude is not linearly proportional to its input amplitude. What does that mean? If I have an input V in here, for a linear system, I expect that the output will be either a certain factor K still times what? V in. That should be my output. So V out should be equal to something like K times V in. That is if the system is linear. But if the system is not linear, I have V in as the input, but the output will be something like K. This K, mind you, may be a gain or a loss. So something like K times V in squared or cubed or something like that. Then this is nonlinear. And therefore, system is said to be nonlinear when its output amplitude is not linearly proportional to its input amplitude. Again, if the system is linear and I have two input V in 1 and V in 2, the output should be proportional again to what? V in 1 plus V in 2. So when the output is proportional to the sum of V in 1 and V in 2, we say the system is linear. But if it is proportional to the squared or cubed or something, then it's nonlinear. Okay, so again, when its output phase is not linearly proportional to its input phase, we say the system is nonlinear. Now, gross nonlinearity will result from cutoff and saturation effects. So when the system has reached saturation or cutoff, then gross nonlinearity will occur. And when there's gross nonlinearity, there's usually gain, compression, and intermodulation distortion. What is gain compression? Gain compression, you will realize that even though you are increasing the input, the output is not increasing corresponding to the input because of the saturation. There's a gain compression there. I had a particular experience when I was working with some amplifiers in a measurement. What I was measuring was noise, and this noise, of course, is very low, and therefore I needed to amplify the noise so that my receiver, which the receiver, which is a noise figure measuring system, that is noise figure analyzer, so that it can detect the noise. So I used two amplifiers. Initially, I used one amplifier. Still, the noise was not high enough to be detected. Then I used two amplifiers. And when I used two amplifiers, I realized that the gain that I'm getting is no more than the gain of the initial one-stage amplifier. And that was very surprising because now I'm using two amplifiers with the same gain. The first amplifier had a gain of 16 dB, and the second amplifier also had a gain of 16 dB. So I was expecting a gain of about 32 dB, and therefore my output signal must increase by about 16 dB. But that was not the case. It only increased marginally because the output of the first stage is now becoming too high for the second stage amplifier. And therefore the second stage amplifier is driven into saturation, and there's gain compression, and also it will result in what? Intermodulation distortion. And we'll see what is called intermodulation distortion briefly from now. So in most active device, nonlinearity is usually due to amplitude-induced change in device transconductance. And this is modeled as a collector or drain current as a nonlinear function of the input voltage, V in. So if you look at this equation here, the output current, I naught, which is either a drain current or a collector current, is given by a certain DC output plus, this is the linear output because there's a certain factor times the input voltage, which is V in. So this is the linear output, but the subsequent output are all non-linear outputs. And the output that is proportional to the third order is called the third order output, and it leads to third order intermodulation products. Second order output could lead to second order intermodulation product, but these are not as important as the third order intermodulation products. So the intermodulation products will result in harmonic powers increasing nonlinearly with the input, as we have seen. This is explained in this diagram. So you have the inputs, the input power here on the x-axis or the horizontal axis, and the output power on the vertical axis. So this is the linear outputs, or this is the output characteristics of this system. So as the input is increasing, the output is increasing correspondingly. Until at this point, when any increase in the input does not yield any increase in the output. Why? Because the system is driven into saturation. And when the system is driven into saturation like this, increasing input does not increase output. There's gain compression, as we spoke about. And then you see that second order, which has a slope of 2, and third order, which has a slope of 3, begin to emerge. Why do they have a slope of 2 or a slope of 3? If you take the logarithm of this one to base 10, this will be equivalent to what? 2 times log 10 V in. And the 2, if you want, is the slope, because the equation of a straight line is y equal mx plus c. So this m is a slope here, and it's usually a gain in the equation that represents a system. So the squared becomes a second order term, and the cube becomes a third order term. And so the fundamental here will have a slope of 1 because it's a linear relationship between them. The input is V in, and the output is also corresponding to V in, and therefore the slope is 1. Now at a certain point here, where the system is driven into saturation, if we extrapolate the linear outputs, we see that there's a point at which the difference between the saturated output and the linear output is 1 dB. And this point is usually referred to as the 1 dB compression point. So we trace that to the output, and we get the 1 dB compression point. If we also trace the the intercepts, the point of meeting of the extrapolated second order with the extrapolated first order or the fundamental, where they meet, refer to the output is called the second order intercept point. So the second order intercept point results from the second order nonlinearity or second order intermodulation. Similarly, the third order, when extrapolated and meets with the extrapolated fundamental, they will meet at a point that is referred to as the third order intersect. So a good system is one that has a very high intersect point. That means that, sorry, let's start with 1 dB compression point. A very high 1 dB compression point. That means that this 1 dB compression point does not occur soon. in the fundamental, it may probably go all the way up, and then the intermodulation products will also go all the way up. But a system that has 1 dB compression point very low, intermodulation products very low, or intercept point very low, means it's a poor system. That system will not give you much what we call dynamic range. As soon as you start operating the system, a little increase in the input will result in saturation and cutoff, and that's not a very good system. So when you look at the data sheet, you'll be looking at where does the 1 dB compression point occur in the system, where does the second order intercept point occur, and where does the third order intercept point occur. And this you can use to judge whether the system is good or not, in addition to the receiver sensitivity and the receiver noise. Other measure of nonlinearity also includes what? Adjacent channel power ratio. What is adjacent channel power ratio? If this is your frequency scale, and then you have the fundamental, we are looking at the frequency spectrum. So the fundamental, and then let's say this is the third order output, for example, or second order, and then you have the third order outputs like that. What is the ratio between the desired signal and the intermodulation products? That is called the adjacent channel power ratio. So the adjacent channel power ratio are the adjacent channel power are those that are closest to the desired signal. So that's this one and this one. What is the ratio between this and the desired signal? That is also called the adjacent channel power ratio. And it also tells you how high the desired signal or the fundamental is compared to the nonlinear output or the intermodulation outputs. So the receiver dynamic range is a difference between the minimum detectable signal and the maximum signal. What is the maximum signal? Is a maximum output before saturation is reached. So if you look at this diagram, this is the fundamental output. At this point, it begins to depart from the linear output. And the third order intercept point occurs here. The second order intercept point occurs here. Now you realize that the minimum signal is determined by the receiver noise flow. So this is the receiver noise flow. And the difference between the minimum detectable signal and the maximum detectable signal, which is here, is called the dynamic range of the receiver. But there's another measure, which is SFDR, or spurious free dynamic range. The third order intermodulation product and the second order intermodulation product give rise to what is called spurious responses. Now there's a region of the fundamental during which no spare is encountered. Spare is spelled S-P-U-R, spare. And this is what gives rise to spurious response. So in the region where no spare occurs, that is this region, from this region all the way to this region, it's called the spurious free dynamic range. So that is, if you're looking at the input, then it is this region here, from here all the way to this point. That is before third order intermodulation product begins to emerge from beneath the noise floor. And that range is called the spurious free dynamic range. I think last week we were almost done when we went off, but here we are, we're still talking about system nonlinearity. There's something called the automatic gain control. So the system or the receiver will usually increase its gain automatically if the signal level is falling below the desired detectable signal. and it will reduce the gain if the signal level is going too high, because if the gain is not reduced, then the system will be driven into saturation and there will be gross nonlinearity. So this action is called automatic gain control. Now, automatic gain control has to be traded off sometimes with noise performance of devices like LNA and so on and so forth. Why? Because as you are increasing the gain, you are also increasing the noise, because the noise is also multiplied by the gain of the receiver. And therefore, sometimes you have to make a trade-off between the gain and the noise performance of the receiver. So when you are reducing the gain, for example, of the receiver as a result of the fear for saturation, the gain is reduced, but it could worsen the noise figure of an LNA, because for an attenuation, it's a loss. Any loss is translated to a noise figure. So a loss of 1 dB will be translated to a noise figure of 1 dB. And therefore, reducing the gain would also translate into increasing the noise figure, which can worsen the noise figure of, say, a low noise amplifier in the system. So this is a demonstration of AGC, or automatic gain control. So here you have the detector. If the detector is detecting very low signal level, it gives a feedback system to the amplifier, and the amplifier will increase its amplification. If that is not enough, the first stage amplification is also notified from this detector. Initially from this detector, the first stage amplifier is notified. But if it gets here and it is still low, from this detector also, it is notified, and then they increase their gain so that the outputs will be intelligible. Now this is a second stage or a dual loop AGC system, and it functions similar to what we explained before. So you have loop 1 of AGC detector system here, and then loop 2 here. And basically what you realize is that this one here represents multiple IF stages. So multiple IF amplifiers are in this stage. But there's usually a feedback that tells the receiver through the AGC loop whether to increase the attenuation here or to decrease the attenuation here in order to increase the output. The same thing with this level of the AGC. And as we discussed, an increase in attenuation here in order to decrease the gain will translate into an increase in the noise performance or in noise of the system. The other important parameter is selectivity, which refers to the ability of a filter to reject signals outside its passband. And now you are designing some filters. One of the figure of merit, or the main figure of merit of the filter, is the selectivity. And we spoke about the attenuation in the filter. So if you have a low pass filter, for example, what is the attenuation in the stop band? Is it like this? Or is it like this? So this attenuation in the stop band is what you describe as the selectivity, because outside of that band, is it allowing, if this is the band, for example, FC here, it means that this filter is allowing something to pass through outside of that band, because attenuation here is not good enough. And therefore, for channel selection filters in radio receivers, we require a selectivity of about 60 dB to about 80 dB. That will be adequate as good attenuation in the stop band. So again, when you're looking at a radio receiver to procure, it's not just the sensitivity, it's not just the system nonlinearity, it's not just the noise performance, it's also the selectivity of the radio receiver. Sometimes it is also measured in terms of the relative strength of adjacent channel compared to the desired signal. So yes, some adjacent channel come through, but how do they compare to the desired signal? And usually a 60 dB compared, C here stands for compared. to 80 dB compared is acceptable as good selectivity. So now we spoke about intermodulation products, and these intermodulation products give rise to spares, which are usually seen in the system as spurious response. So the spurious responses are outputs that arise from unwanted frequency components. And so we're giving an example that if you're demodulating a channel whose carrier is at 895 megahertz, it is possible that a signal at 890 megahertz can create a response in the receiver, which will interfere with a channel at 895 megahertz. So this signal which interferes is called spurious signal. And this spurious signal can reduce the selectivity of a receiver because it can combine with intermodulation products, and then the combination will result in signals which will fall directly on the frequency of the IF, and therefore they will pass through the system. Though it is coming from an undesired signal, it is not filtered out, and then it makes the selectivity of the receiver to be very poor. So here we are looking at the way currently there are, if you want, softwares or systems that are used in design. When you are laying out your network, which frequencies you assign to which nodes, there are softwares that allow you to do that very easily in a way that you can avoid a lot of spurious responses and therefore interferences to your system. But before that became available, then this was the manual way this was treated. We identified these three frequencies. We have FT, which is a desired signal. Then we have FS, which is the unwanted spurious signal. So in the mixer, FT and FS will mix, and they will give rise to the output at the IF. So sum and difference frequencies will be produced with the mixer's LO frequency, that's F0. So for a sum mixer, F0 with the tuned frequency will give you FIF. For a difference mixer, is F0 minus FT will give you IF. And for a different mixer with low side LO, so since LO is lower than the FT, this will give you negative FIF. And a negative FIF is nothing but a frequency inversion. Now, when you have spurious signals coming into the system, they can also mix with the oscillator at multiple harmonics. They can mix with the oscillator frequency at multiple harmonics, which are denoted by N and M, to produce a frequency that is also equal to the IF. So if the frequency here, as a result of the multiple harmonics combination, gives you FIF, it cannot be distinguished from the actual FIF in the sum mixer or the actual FIF in the difference mixer. And therefore, even though this is coming from a spurious signal FS, it can pass through the system, and the selectivity of the system will become very poor. So for a sum mixer, we have NF0 MFS equals FIF. For a different mixer, NF0 minus MFS equals FIF. And for a difference mixer low side oscillator, NF0 minus MFS equal to minus FIF. Now, if we normalize by the IF, then we use T to be equal to FT divided by FIF. O would be F0 divided by FIF, and S would be FS divided by FIF. Now from here, we can eliminate O. How do we eliminate O? From here, FO is equal to what? FIF minus FT. So FIF FIF, if we normalize it, that is divided by, again, FIF, that will be equal to 1. And then T normalized is, FT normalized is what? FT over FIF. So that becomes T here. And therefore, O will be equal to 1 minus T, because here, FO is what? FIF minus FT. If you normalize them, then this will become O. O will be equal to, this normalized is 1, this normalized is T, minus T. So 1 minus T. And therefore, instead of O here, we have 1 minus T. Instead of O here, we have 1 minus T. And therefore, the new equation becomes N 1 minus T plus MS, where S is a spurious normalized, or the spare normalized, equals 1. Because this is FIF, when you normalize it, it becomes 1. So that is for the sum mixer, and for the difference mixer and the other difference mixer. So these are the equations. Now you can see that this is the equation of a straight line. How is it the equation of a straight line? If this is the normalized interference frequency, so if we divide through here by M, for example, this is N over M. So this becomes like Y equals MX plus C, where C here will be the 1 here, that is divided by M. S here is Y, and then this one is the MX. So this can be plotted, and when they are plotted, you get series of straight lines like this. So in the past, what they will usually do is that they will identify that this is the desired frequency. So they will find out that which one of these spares will map to the desired frequency. And that is the space that must be eliminated so that it doesn't interfere with the signal. And that explanation is what is provided here. But these days, these are no longer used. There are softwares and computer-aided design packages that can tell you which signals are likely to interfere with your desired signals, and therefore the design will make appropriate adjustments so that this can be avoided. So this is a typical example of a CDMA receiver handset, which some of you are using. And everything that we have discussed so far comes together here. So you see that there are 2 blocks. Where are the 2 blocks? We have this block here, and then we also have this block here. So these 2 blocks represent the transmit path and the receive path. So let's try to identify all the components in the CDMA receiver handset front end. Here you have the antenna, of course. And here there are 2 filters. These filters are called diplexes, because there are 2 filters which have different frequencies or different frequency band. So when the incoming signal comes, it is this filter here that is designed to allow the incoming signal to pass through. And therefore that signal will go through the transmit or the receive path. In the receive path here, you have this IC, which is MAX 2338. And you can see in that IC, what we have here are what? Amplifiers, RF amplifiers. As amplification, there is this bandpass filters. How do you know that it's a bandpass filter? Because of the symbol. The symbol is this, and then up there cut, lower there is cut. So only the frequency between the higher and the lower frequencies pass through. Therefore, it's a bandpass filter. So you have a bandpass filter here, and from the bandpass filter, it comes to a mixer. And this mixer has its local oscillator supplied by this combination here, which is more or less like a frequency synthesizer, which is amplified, and it comes to the mixer, and the mix output is also amplified. Now you can see that each path has what? Some form of redundancy, so that if there is a failure in one path, it's taken over by the other path. From there, since it is a receiver, this bandpass filter would select the lower frequency, i.e. FO minus FT, or FT minus FO. This will be selected. It is amplified again by this IC here, and then there's a second stage of mixing. After the second stage of mixing, the frequency is lowered again, and then filtered again by these bandpass filters, amplified, and it goes through other processing, and then it is detected. And the transmit path is exactly the same thing, but in the reverse direction. Now let's look at some of the parameters of this CDMA receiver as we have discussed. So these are the air interface specification for the CDMA receiver. Receiver frequency band is 1930 to 1990 megahertz. And transmit frequency band is 1850 to 1910 megahertz. And the peak frequency division that is allowed is 1230 kilohertz. The maximum input power is minus 25 dBm, and the total power at the antenna connector, that's minus 25 dBm. So what it means is that if you allow, or if the signal goes above 25 dBm, then it means that it may drive the system into saturation, unless of course it uses its automatic gain control to manage it. The minimum detectable signal is minus 104 dBm. And what is the minimum detectable signal? Is a noise floor referred to the input. If you remember, when we discussed the minimum noise floor, it was minus 107 dBm. So 107 dBm, it means that minus 104 dBm is really very good. This is really very good. Which is why the CDMA can actually have a very good performance of a low signal to noise ratio because it has a higher bandwidth, and you can see that the noise performance is also very good. Then detection in the presence of low level interference is also minus 101 dBm, which is also very good. That is in the presence of two tones at minus 43 dBm, offset 900 kilohertz and 1700 kilohertz. This is what I was talking about earlier. So you have this. So this here at, let's say, minus 43 dBm at 900 here, and then another one at 1700. If their level is at minus 43 dBm, it is able to provide a good detection for a signal that is at minus 101 dBm. The output power is 23 dBm to plus 23 dBm to minus 50 dBm. And then you can see the dynamic range from the lowest to the highest. So the dynamic range here is about what? 73, if you look at it. 73 dBm. Maximum adjacent channel strength is minus 42 dBm comparative to minus 43 dBm. So it means that if it goes above minus 42 dBm, then there'll be a problem in the system. Maximum alternate channel strength at 1980 kilohertz offset is minus 54 dBc. You remember we call the ACPR, which is quoted in dBc. So this is an example of the specification of a receiver handset. But some of the things that we discuss are not seen here. For example, the sensitivity is reported. Where's the sensitivity? This is the sensitivity. It's reported here, but the selectivity, for example, is not reported. And a few other things that we discussed were not reported here. So basically, if you're an engineer in a company and you're going to procure a radio system, these are some of the parameters that you should look at in order to make a judgment. There's another simplified CDMA receiver handset. Another part of it. This is a core component of the digital part. In the digital parts, you have the antenna. Again, it goes through a duplexer. And then the LNA. Why do we have LNA here? Because even though the signal needs to be amplified, it's amplified together with the noise. And so when you use an LNA here, low noise amplifier adds usually very little noise from its own internal noise. And therefore the output noise is not as high as it will be if you had used an RF amplifier here. This one here is RF image reject filter. What is an image? An image is what we discuss here as a spurious signal that will create an IF. So if the combination of the spurious signal will create an IF, that spurious signal is called an image frequency. It is the image of the desired frequency. So this filter here is designed to reject that image frequency. And then you have a mixer, and after an LO frequency mixes with the incoming signal, you get the output which is filtered, and then you have the IF, which is amplified, and it goes through this digital stage. So in this digital stage, there are two arms. This LO here supplies, let's say, a cos omega t signal, and because it is shifted by 90 degrees, we have a sin omega t signal here. So the cos omega t signal will pass through what we call the I channel, that's the in-phase channel, and the 90 degrees shift, which is a sin omega t signal, will pass through the Q channel, which is the quadrature channel. So we have the in-phase channel and the quadrature channel. This in-phase channel will produce the 1 bit, and the quadrature channel will produce the other bits. So let's say this will be 1 and this will be 0. And the 0 and 1s become the digital signal that is produced from the system. So this is the end of the presentation. If you have a question, you can raise up your hand, and I'll call you, and you would unmute your mic, and then you ask a question. Yes, Derek. Derek,
yeah. Yes, sir. Please, between CDMA and then GSM,
yes.
Apart from the fact that they use different frequencies, or the bandwidth, which is preferred? Which one is good?
CDMA. If you know that CDMA is code division multiple access, in addition to its good performance in terms of, because it has a high bandwidth, so the channel capacity is good even with a low signal to noise ratio, the coding is used such that even though the signal is very low and the channel capacity is low, the errors that would have been introduced are taken care of by the coding. And therefore, there are minimal errors that are introduced in the system, and therefore the system performance is generally good. So CDMA is a lot better than GSM.